Section 1.6 is titled Formal Definition of a Limit. When we very first started talking about limits, and to this point thus far, every time we talk about limit, the phrase that I keep using is something like this. It's a value we can get really, really close to and we may or may not touch. Right? Intuitively, that really makes sense to us. We can sort of get our minds around that. We can kind of grasp onto that. We can think about that in such a way that the pieces sort of start to connect. Okay? Even if they didn't right away, that language starts to connect. But that is definitely not a very formal definition. I mean, have you ever heard anything math that sounds like that before in a textbook? Probably not. So this is the section where we're actually going to pin down the formal pieces of what this looks like. And I'm going to do it in a little bit different way than your textbook, just to kind of develop the idea of it a little bit better. All right, so it says to consider a function that you know. This function is f of x equals 5x plus 2. What does this graph look like? A straight line, right? Well, lines are always going to be straight, but yeah, and it's actually diagonal in this one, right? Diagonal line. Okay, so we got a diagonal line. It says to consider finding the limit as x approaches 3 of 5x plus 2. Now, you know how to do that. You can just plug the number in, right, in terms of algebraically working through the problem. What did you do? Well, you put in 3 for x, and you'd end up getting 17. No problem, right? Okay. It says, although intuitively this makes sense to us, the description is imprecise. And we're going to consider the graph, and we're going to talk through how that actually works on a graph. So graph yourself. That's not what I wanted. Let me try that differently. Okay, so we're going to draw ourselves a graph. And we're going to do our best to sketch it in such a way that it's maybe believable to be the 5x plus 2, but I'm not terribly concerned that it's exact, okay? So we're going to look something like this. I didn't even put a scale in, so it's believable, okay? All right, so we're looking at x is approaching 3. So for the sake of my diagram, in fact, I'm going to change it up just a little bit so that I have a little bit more space to work. For the sake of my diagram, we're going to say that this right here is x equal 3. And if we went up here, right here, then what I'm saying is that that's 17. Okay, is everybody good with that? That's just basic algebra kind of graphing, right? So far, so good. All right, so what we're going to do, I'm going to go to the next slide here, is it said, let's say we want to make sure that the function value and the limit of the function are both approaching 3. Like when you physically plug the number 3 into it, you're really just finding out what that ordered pair is at that particular point, right? You're not really finding a limit. You're really just evaluating the function. So let's say we want to make sure that the limit and the function actually work. They are actually both approaching 17. And perhaps we want them to differ only by 1 unit. So if so, how close of an x value to x equal 3 is required to ensure that the limit between 5x plus 2 and 17 is less than 1? So let me go back to the picture. What we're saying, what that is all saying, is that let's say, for instance, we want to make sure that we're really close to 17 on the y-axis. We only want to be 1 apart. In other words, we really only want to go up and down between 18 and 16. Okay? We want it to be tight, within 1 unit. The question is, how tight would it have to be down here on the x-axis to make sure that we were within 1 unit? And I'll tell you, most of the time it's not just 1. In fact, let's give it a try. Let's say we put in x equal to 2. If you put x equal to 2 into this function, what do you get? 12. Is that between 16 and 18? No, it doesn't work. So you can't just say that the distance on the y-axis is going to equal the distance on the x-axis. There's got to be something else going on. Okay, so let's figure out how it is we figure that out. Well, we want the y value of our function, which is 5x plus 2, and the y value of the limit that we're hoping that we're around, 17, to be really close. We want them to be within 1 unit of each other. That's the 16 to 18 business that we put in a minute ago. Everybody good so far? So in other words, what we want to figure out is we want to figure out how tight the x minus 3 has to be. That is the distance between x and the distance between the x value of 3, how close those need to be on the x-axis. So how do we do that? Well, here's what we do. We take that inequality that I've got a mess on right now. Let me clean my mess off. We're going to take this inequality right here, and we're going to solve it. Okay, a little bit of algebra. So the first thing we're going to do is we're going to simplify what's inside of the absolute values. So what is 5x plus 2 minus 17 simplify to? 5x minus 15. Everybody good so far? Fabulous. All right, the next step is that we're going to notice that the 5x and the 15 have something in common. A 5. And what we're going to do is we're going to factor it out in front. Now, because the 5 is already positive, it can factor out of the absolute values without changing anything. If it were a negative 5 they have in common, and I factored it out of the absolute values, what would the negative 5 become? Positive 5. So be aware of that. We are factoring and doing an absolute value at the same time when we did that. Okay, so this is less than 1. Oh, yeah, no, I have that, right? Okay, good. And then, again, the goal, if you take a look over here, is to get an inequality that says absolute value x minus 3. We're close. What needs to move so that I actually have absolute value x minus 3? The 5. How do I move the 5? I divide. Fabulous. Okay, so we're going to divide both sides by 5. And, of course, that cancels out the 5 that was in front. That leaves me with x minus 3 in absolute values, less than 1 over 5. So in this picture over here, what does that mean? Well, it means right here around the x value of 3, the biggest difference we can go to the left or to the right is 1/5. You guys with me? So what that really means is that this number right here is 3 1/5. We'll write it in mixed number form for the moment. And this number right here is actually 2 4/5. We're just 1/5 to the left and to the right. And as long as we're within 1/5 on the x-axis, we will be within 1 on the y-axis. That's what the limit's saying. A limit actually says that no matter how big of a difference that I make around the y-axis, and there's nothing special about the number 1. I could have made the number that we differed the 17 by, I could have made that value 0.2. Right? I can make it as tight as I want. That no matter how tight I can make it, I can find that little interval around the x-axis that will still be tight enough and make it work. Okay, so let's extend that idea.
I have a question.
Yes.
At the beginning of that, the 5x minus 15, where did that come from again? Is that just...
All we did was we combined the positive 2 and the negative 17. So we add those two together. We're just simplifying what's underneath or inside of the absolute value. Yeah. Okay, any other questions before I jump ahead? I'm sorry, I should have asked. Yes?
How do you get the numbers? Like what do you do after you have the inequality simplified like that?
Like with the very end of what I'm looking at right here, this value, this value right here would be the answer to my question of how far off I have to be. Right now, we haven't actually done a problem that looks like your homework yet. We're very close to doing one, though, and then you'll see what the answer, how that process actually plays out. Okay? All right, let's take a look then and notice what this says. I said it already, but let me say it again. The number 1, that is, we want the 17 to be within 1 unit. That was arbitrary. There's nothing special about 1. I just used 1 because that's what I chose to use. Okay, there's nothing special about the number 1. We could have chosen any value here. So since we can choose any value here, we are going to choose an arbitrary value. And the value's name that we're going to choose is epsilon, Greek letter epsilon. Okay? Kind of looks like a script E. Now, it needs to be positive. And think about that. That should make sense. Right? I've got the number, and I'm talking about a distance away from something. So obviously, we've got to talk about something that's positive, or it doesn't make any sense. So we're talking about epsilon. We do use the letter epsilon because epsilon means small number for mathematics. Anytime you see an epsilon, you're talking about something that's small. So that's why that's being used here. Okay? So let's go back to the same problem. 5x plus 2 minus 17 in absolute values. Instead of being less than 1, it's less than epsilon. Okay? But it doesn't change any step we did in the process. We still simplify inside the absolute value. We get 5x minus 15. We still factor out and then take an absolute value of the 5. And we still divide by 5. So we still end up getting absolute value x minus 3. And in this case, what's on the right then is a value in terms of epsilon. It's epsilon over 5. And we give this epsilon over 5 the name delta. So as you hear others working through this section, or as you hear the tutors in the Success Center, you might hear them refer to what you're doing as epsilon delta proofs. show you what we mean by proof in a minute. But you very well might hear them call these epsilon delta something, okay? So just be aware of that happening. If that's what they're talking about this section of material.
So our answer is the epsilon over 5?
Yes, the epsilon over 5 is part of the answer. I'm going to show you how we write out the whole answer in the next problem. But yes, the epsilon over 5 is what we're looking for anyway. Yeah. All right, so here's actually the formal definition of limit, finally. After all of that first page of developing what in the world we mean by that, this is the formal definition of limit, and you are going to memorize it. Because I will guarantee on your very first test, I'm going to say, write down the formal definition of limit, and as much as I would like this not to be true, somebody in this class is not going to memorize it. And it's going to be so sad, because you're just going to flat out lose 5 points or 6 points or whatever it ends up being on the test, and that's just not necessary. Because I'm telling you right now, you should memorize it. Okay? So here's the deal. For a function f defined in some open interval containing a, but not necessarily at a itself, we say that the limit as x approaches a of f of x equals L. If for any epsilon greater than 0, that means any distance around the limit value, there is another number delta greater than 0, that means the distance around the x value, such that if you're really close on the x-axis, you're going to be really close on the y-axis. That's all this is saying. It's just doing it with math notation. So, if your absolute value is between 0 and delta of x minus a, then you're guaranteed to have your function f of x minus L, absolute value, less than epsilon. Okay, I think all of you have it written down. If you're not quite there, you can go back and look later, or it's in your textbook too. Okay, the directions are going to say the following. This looks exactly like the directions in your book. Symbolically find delta in terms of epsilon. I'm going to ask you to do two things. One of the things is exactly this direction, but there's one more step at the end that you have to do. So be careful when you're doing these homework. Be careful when you get to this problem on the test, and you'll have something like this on the test, that you remember this is a two-part process. Okay? 2 steps. First step looks exactly like what we just did before. We're going to take the values that we've got, everything going on here, and we're going to do these absolute value things, and we're going to get an epsilon and an answer. Okay? So we're going to do that first. Now, this doesn't have all of the absolute values and stuff in there like the last one I did, right? So let's think about how we got to that point. Well, how we got to that point is we figured out what in the world we thought the limit value was. So in other words, if I plugged in -2 here, I end up having a -4, right? Okay, so even if I hadn't told you the -4, we could find that out. Agreed? Okay, so thinking in terms of absolute values, what we want is we want the absolute value of the function, that's the 3x plus 2, minus the limit value, in this case, -4. So it's always function minus limit. Go back over here and take a look. See that right there? Function minus limit. That's what we're doing. Function minus limit. And we make that less than what? Epsilon. Always less than epsilon. And you see that right here? Less than the epsilon. So this step always looks like function minus limit in absolute values less than epsilon. Now we're going to do algebra. This is an algebra problem. It's not even a hard algebra problem because we don't even actually have to figure out what is x. So that's kind of cool. We're just going to simplify what's in the radical at the moment. So this is 3x, and then what? Plus 6 is less than epsilon. We look at the 3 and we look at the 6 and we notice what? We can factor something out. What can we factor out? A 3. And the absolute value of 3 is 3, so it really does factor out plain old 3. And what am I left with? X plus 2. Don't forget to divide the 6 by the 2 as well. Okay, what would I do next? Divide by 3. Fantastic. So I end up with x plus 2 is less than epsilon over 3. And here's the beauty. If you did the algebra right, if you factored right, if you simplified the addition right in there and so forth, what you will always end up with is the x value minus what the x value is supposed to be approaching. Do you see it? This should be, where we end up at this point should be x minus -2. And is that where we ended up? Yes, it is. This is the symbolic delta in terms of epsilon that we were asked to find. Okay? So in terms of the question as it's exactly stated, this is it. But this is not done. Here's the second step. The second step that you're going to do is you're going to write down what in the world it is that you did that makes you know now for sure that this limit really works. So it looks something like this. We can say, or we know that, or this shows that, any of that kind of stuff. We can say that the limit as x approaches -2 of 3x plus 2 equals -4. We know that's true. Why? Because for any number epsilon greater than 0, there exists a delta. And what is our delta equal to here? Epsilon over 3. So this is what we put in here, right? Delta equal to epsilon over 3. Such that when the absolute value of x, I'll put minus -2. You can put plus 2 there, that's fine. But when the x value minus the x, what it is approaching, is less than that epsilon over 3, this guarantees or shows us that, or confirms, or whatever language you want to put in there, guarantees that our function value f of x, actually we could write f of x in there. I'll write our f of x function. We had 3x plus 2. That our function value 3x plus 2 minus the limit value -4 is less than epsilon. Think back to that graph. What in the world is this sentence saying? This sentence is saying that I was able to actually isolate a small area, a small space, a small length along the x-axis. And because I could get this length along the x-axis, it guarantees that I've got a really tight length along the y-axis. That's all this sentence says. It's got a little bit of math lingo in it, but that's what it says. It says, I've actually been able to show that this works. That I don't have anything weird going on around my value -4. It's really the right value because I can make the values around the x-axis tight enough that the values around the y-axis will also be very tight. You guys okay? Now, in reality, what does it mean? Well, I really hope that you're catching on to the understanding of this, but I also know that you're going to have to probably do a little bit of work on memorizing this phrasing because the order of it matters. If you switch, for instance, the two inequalities, it changes the meaning of everything. Right? Knowing that something's really tight along the y-axis makes it tight around the x-axis is the wrong direction of what we're trying to show. You know, the order of these things matters. All right? So yeah, is it going to mean you're going to memorize a little bit? Yeah. But you know what's kind of cool? If you memorize this, it's almost exactly the same language that I just wrote down, isn't it? Really is. So these two things go hand in hand. If you memorize one, you probably will have to memorize the other one quite easily. So let's try one more of these. Okay, directions, same thing. Say, symbolically, find delta in terms of epsilon. So this one, however, does not quite look like the last problem. Why not? There's a fraction in there, right? This does not look like a linear equation. The last one was even a line. I mean, really? 3x plus 2? And now all of a sudden we have x squared plus x minus 2 over x minus 1. Okay? But fractions don't always create as big of problems as we want them or think that they will. We might be able to factor something, and that's where we're going to start. So let's take a look at what we have and see if there's a way to simplify what we have to make this friendlier. In particular, does my numerator factor? Yes, it does. How does it factor? X minus 1 and an x plus 2. Why is that valuable? Yep, it reduces the x minus 1. Notice that x minus 1, when it reduces that way, what happens when I'm able to cancel that out like that? There's a hole, right? We have a hole in the graph at x equal 1. The reason I bring that up, or there's a couple of reasons, but one of the reasons I'm bringing that up is because notice this says up here, but not necessarily at a itself. This one right here has a limit, very, very close. I mean, like it has function values very, very close to x equals 1. But it really does not have the ability to plug in 1, right? I mean, it really does not, this limit, I mean, this function does not exist at x equal 1. And that's okay. It's really not a problem. Okay, so it doesn't have to actually exist there. Okay, so we reduced this just fine. And we notice then, of course, here that we end up with a reduced form that says something like the limit as x approaches 1 of x plus 2 equals 3. From this point, it actually looks a lot like this problem now, doesn't it? It really does. So that's where we're going to take this particular one from here now. So what do I do next? Absolute values. What's going to go inside my absolute values?
Plus 2
Mm-hmm.
minus 3.
Fantastic. Everybody good with that part? Oh, thank you. I was already ready to talk about the 3 apparently. Oops. All right, that's better. What's going to go on the right-hand side of this? Less than epsilon, right. Okay, simplify what's inside. What do I have? X minus 1. And the cool thing about this is what? That's it. I mean, we don't even have to do any dividing like on the last one, right? Okay, so you don't always have something you have to divide out. This one we didn't. Well, I guess technically we divided out the x minus 1 at the very beginning, but we didn't have to divide out a value 5 or something like that on this one. Now, again, I mentioned this before, and it is still true, so let me mention it again. Notice these pieces, they go together, right? It's x minus what x is approaching, and they will always do that unless you've made an error. It has to work like that, okay? So we actually found out that this epsilon, it is our delta this time. The answer at the end actually ends up being the same thing that it was before. Like the epsilon didn't actually get affected, right? Like notice down here at the end, we give this value at the end, whatever we ended up with, a new named, the name is delta. What does that mean in terms of a graph? Well, it means that however far away you were on the y-axis, you're that far away on the x-axis. Like my original example, right, was between 1 and negative, 1 and above and 1 below, and I had to be within 1/5. Well, on this example, if we were looking at this graph, 1 above and 1 below would correspond to 1 above, 1 to the left and 1 to the right. That's all that's saying. It's really not anything different than that. It's just saying that we have a little bit more play with room kind of thing. Yes?
So, can't we just from the beginning use the, like, as x approaches the number and find the answer from that? You know what I'm saying?
Find,
Like,
oh, I'm sorry, I think I'm on the other screen. This one right here, is this one you're referring to?
yeah, well, like any of them, you said it's the same.
Well, this one, the epsilon and the delta are the same value. But like on this one, the epsilon and the delta weren't. We found out that delta was epsilon over 3 on this case. So sometimes they are going to be the same as possible, but it certainly doesn't have to be the case. Okay? Let's work through the written down part of what this looks like. This is the part where what you're actually writing right here is a proof. Okay? What you did already over here, this work is not a proof. It's finding what the value is that you needed to write down so that you'll be able to write your proof properly. And this is like a one-sentence proof. That's what you're doing. So we can say something like this. I'll change my language up a little bit. We know that the limit as x approaches 1 of my original function, which was x squared plus x minus 2 over x minus 1 equals 3. We know that. And then we have to say why. Because for any number or every number, any value, epsilon, greater than 0, there exists delta equal to what in this case? Epsilon. It actually equaled epsilon in our case. There exists a delta equal to epsilon such that and again, I'm changing my language up just a little bit because I don't want you to think there's something very super special about any of my specific words. I mean, like there's other ways to write this. Such that when or if when the absolute value of x minus 1 is less than that epsilon, right, this epsilon right here, and it's the delta value. Maybe I shouldn't write it like that. I don't want you to think it's multiplication. But it's the epsilon that's coming from here, right? When an absolute value of x minus 1 is less than delta, then the absolute value of my function, written as a whole, which means x squared plus x minus 2 over x minus 1, minus 3, the limit value, is less than epsilon. And this epsilon here at the end is the epsilon right here that we originally encountered. That's where that came from.
So we need to specify which epsilon we're
You don't. The reason I'm mentioning it is because it looks funny on this one because there's so many epsilons. And what I don't want you to do is to switch the epsilons for delta, or to switch the epsilons around if you had something like an epsilon and an epsilon over 5. It's easier to see over here, right? Because they don't match. One of them really is epsilon over 3, and one of them really is epsilon, and they really are different. So that's why I make mention of it.
So our answer for this one will be epsilon and then our sentence.
Correct. So when you're doing your work is going to look like this. You're going to have some algebra work over here with inequalities, the end of which is going to be something that looks like x minus 1 is less than epsilon equals delta. I mean, it's going to be the ending line of that. Your work may not be as detailed through there, if that's okay, but the end result has to be that inequality. And then you have to write this sentence that says, what in the world does this mean? What does this tell me? How in the world is this useful? What does that have to do anything with this formal definition business? And that's what you're looking for. Okay? All right, so here's what's going to happen next.